Okay, we continue this one. I will come back with this derivation in next lecture. But we continue from this example one. We need to use the delta xb and delta xy. So for the equation 1 and 2, I will come back for more detailed explanation. Right? Um, okay, what is important is there is a parameter you need to use, which is xb, delta xb, and delta yw. Okay, I'll come back to this one, equation 1 and 2, how you derive it. Okay. So it is seen that the sign of this equation and indicate in the figure an increase of delta, this one, an increase of delta will cause a decrease in xb and increase in yw. So it means the more the more you go down, y will increase, but there is a xb, this one, the xb here will become shorter and shorter. Okay. Okay, means this one will decrease. XB, this one will decrease. The YW will also increase. Okay. Equation 1 and 2, I'll come back in next lecture. All right. So you do the virtual work. So virtual work equation, again, work vector must same as parallel to the direction. So you get positive work. So if virtual displacement XB and XYW is positive, so this one, XB, you know that to the left is positive, right? Sorry, to the right is positive, because in this case, there is a negative sign there. Negative sign means this one go to the left. Okay. So if you assume both positive, force W and the force, the weight and the external force will do positive work or negative work. You look at W, this one you didn't know already lah. F will do negative work, W will do positive work. Okay, sorry, will do positive. Oh, because this one, why? You assume XB and SW both positive. This one, when you have this assumption, then both will do positive. So we assume all is positive. So W, one arm is W delta Y. You do work, W and the displacement do work. You have two arm there, so you have two entity. And F delta X XB equals 0. Okay. Recall these two equation already derived. And the partial differential of XB, XYW, I will come back in next lecture. So you substitute these two inside here and factor out the common displacement delta, right, in these two equations. You arrive at this equation. And you can find, okay, you move this one, 50 sine. Okay, this one, delta 0 cannot be 0. Right, you have factor two entity, bracket 1, and this entity, you have two components. This one cannot be 0. So this one must be 0. Right? So this one must be 0. You pull this bracket out. So this one equals 0. You move your 50 sine to the right hand side. You move your cos to the right hand side. You get tangent. Understand? So tangent, you do calculation. The theta equal to 63 degree. Okay. Equation 1 and 2, I will come back next lecture. Okay. Okay. But at the same time, if you're able to figure it out, you can share with the class. Right. Okay. Now, example 2 is the same concept. It looks complex, but actually is if you understand the principle of virtual works, what is work, then you should be able to solve. Focus on one member or the body, right? So first imagine how the object will behave if you under a certain loading like this, right? How will this object, without looking at the statement, you know that when the external force pull P here, this thing will string like this, right? Then this one was locked, A was locked. So this one, when it string, this one, what happened to G? Move up, move down. G, this one, the pin here will move up or move down. If you pull this way, move down. You should be able to imagine this collar here, it will move down because you pull this one, move down. It will be this one string. So this one string move down. Okay. Then there's a spring there. So spring, you know spring force. F spring equal to K multiplied by the distance of this spring move. Okay. And this one, it look like a triangular, lots of triangular. Okay. So triangular, there are two rules, either right triangular or you need to use the cosine rules. You know what is cosine rules? If you don't know, go home, flick the mathematics. Right angled one, you know lah. Right angled one. There's one rules about A, B, C. This one is A, this one is C, this one is B. So you have equal something lah, cos A equal to something divided by something. Okay. Or cos square equal to something. Go and look at this one. So you try to figure out how it behaves when you have an external force pulling to the right. So you draw before and after. You draw a diagram before and after. Basically, you don't need to draw this one. You just need to try to imagine how it happened. So in free body diagram, draw the bodies and then try to imagine how it works. So when it happen a D, a P, external P, it will move down. The point C will move down, point E will move up. G will move down. S spring will pull to the left. Why pull to the left? This is imagine your point B. What do you feel? You feel the spring punching in or pulling out? Pulling out. So the arrow is pointing up to the left. We remove the spring, but imagine what if you are the point B, what do you feel? A is pinned to the ground, so you have two reaction force there. Okay. At this point, it doesn't matter. For example, A, it doesn't matter whether point to the left or right, but always it's highly recommend you fix to one direction you prefer, so that you know how to solve. Right. So this one is just pointing out. It's just spread out all the force. Right. You might ask, Dr. Can I point inside or not? Can. It's just that at the end, if you get negative, you need to flip the direction. Okay, this is your estimation. Why the G is like this? Why the G is only one force? Because it's a collar pin. Collar pin, you only have one contact force there. You point up and down. Okay, it's only one contact all the time. Okay. And the direction of GX, you can point to the right if you want. But at the end, if you get some negative, then you flip the direction. Okay. As you can see this example, the author is trying to split all the force pointing out from the object. Okay, so this is the approach or assumption when you do virtual works. You just spread out the force. Okay, then when you get negative, then you flip back the direction. Okay, which force do work? Which force do works? P do work or not? Yes. Fs do work. A do work or not? No, because it's a pin fixed there. G do work or not? Why? A different direction. You only meet half of the keyword there. Why G do not do work? What happened to the angle? In what scenario work doesn't work? 90 degree. Because G always 90 degree to the distance. Either move up or move down. G always 90 degree. 90 degree doesn't do work. Okay. Yeah, then in your diagram, you just modify a little bit. You copy the initial distance of XD. You draw XD to the X direction. We look at point D. We focus on point D. So you measure from the wall to the interest point D. You establish XD. Then also here, from the wall to point B, you write XB. And then initial angle, you copy from the diagram, theta. Then you improve the diagram with the motion under the effect of external forces. So you know that the object will string, C will go down, E will go up. So there is a changes of distance traveled by P. P will move in the small distance delta XD in X direction. B will move to the right, delta XB, B point will move. And there's a small changes of angle between the arm of AB. They will be moving clockwise, delta theta. Okay, then the rest is the same. Again, why we do not find the distance of your G? Because it doesn't do work. So you can still go and find the distance, but it doesn't make any contribution to the answer. Okay, so then after you do the free body diagram, then you go to the detail. It asks you to require force needed to maintain equilibrium of scissors linkage when theta equals 60. You need to maintain equilibrium, means all the force equals 0, all the moment equals 0, and all the work equals 0. Spring unstretched when theta is 30. So means at the rest or before you start is at 30. So when you pull from 30 degree, this one, pull from 30 degree until 60 degree, the changes of theta is 30. Ignore the mass. So that's why you do not see W inside the linkage. The question relax a bit because it asks you to ignore the mass. Means the W effect of W is taken out. The work, if this statement do not write, then you need to put in W, then W will do work. The W will point down, will do work. Okay, so your equation will be longer. Okay, so in your FIP or final projects, if you design something, or EDP, you design something, don't ignore mass. This is just a tutorial question, so just simplify the things. Okay, PF do works. Okay. Okay. So at arbitrary position theta, spring is stretched. So this one is just a derivation, the distance stretched by the spring. So 300 sine theta is here, the distance stretched by the spring, right? 0.3 sine theta is this distance, is stretched from 30 to 60. By the end, at first you just derive the equation first, right? So sine theta minus 30 original means the distance traveled by the end angle and the early angle. So spring force equal to Ks, then you substitute the equation, right? You'll get one equation first. So for statics or dynamics, don't go and substitute value inside first. Derive the equation, then only you substitute. If not, you're going to miss out the relationship between the unknown. Okay. Okay. So always draw free body diagram. Then find any unknown, especially chapter 6. You know that chapter 6 is virtual work. You need to identify the work, the force, and the distance traveled. These two things. Find the small distance traveled first. Then only you complete the equation. Force equals 0, moment equals 0, work equals 0. Okay. So this one, virtual displacement, xb and xd measured from a fixed point A. For virtual work, we always like to find a fixed point because it's easier for you to make reference. Okay. So xb in this case is this one, xb is this triangular, rectangular. So here to here is 0.3. xb is here, so it's sine. Okay, this one you want to find xb here, so it's a sine. This one and sine this theta. xd is here to here. So you have xd, you have 3 triangular. I'm not sure whether you're able to see. This is 1, then here got 2 triangular. Okay, so when you have a linkage, the angle will be the same. Multiply 3. Yeah. So here for xd, you actually calculating the 3xb. Yeah. This one and then 2 triangular here. Okay. Then delta xb. Delta xb need to think a little bit. Delta xb, this delta xb is here. Yeah, delta xb is here. So is this very small triangular here. Okay, delta xb is 0.3 cos theta. Cos this theta. And xd, this one, is 0.9. Okay. xd is 0.9 because you have 3. Okay. So as you can see, xd and delta xb and delta xd, they are actually related. Delta xc actually 3 times of here. Okay, this one, delta x capital D, is actually 3 times of xp because got 3 set triangular. Okay. Then you solve virtual works Okay, virtual work is force P moved by this distance, spring moved by this distance equals 0. Substitute the equation. You get what is P in the theta. This one. Again, don't substitute 60 inside there first. Then only you substitute. Why we don't want to substitute 60 early? Because you will press calculator, you will remove some of the value accidentally. Try to avoid the careless mistake. It's not accurate. Okay. So the rest you will see is there's a pattern there. There's a pattern. Important that you see what is the steps. Okay. First you draw free body diagram. Then you imagine what is before and after. Find this small displacement. Where is the small displacement? Okay. So in this case, it asks you require force of P. So you focus on point P. But there is something happen to other bodies. So you find the small changes of this one. So you try to relate this one to the small changes of three small triangular. Okay, then you use the virtual work equation, which is all the work equals 0 or partial differential u equals 0. So you either you know that P is to the left parallel to the distance, change of distance, create positive, but the spring create negative work. So positive, negative, then you solve. You know that angle cannot be 0. Then you factor out. Then you solve for the remaining one. Okay. You see, this one also same. Example 3. Example 3, what is different is that now you have moment. So remember to add in moment. Again, moment, how moment create work? You multiply by the change of angle. It will create work. Okay, remember, work, you have two things that can create work: translation and rotation. Translation is because of the external load or force. Moment can create work when there's a rotation. Moment multiplied by the angle, you will create work also. So there are two, force and moment will create work. So here, it gives you a mass of 10 kilogram. Determine coupled moment needed to maintain equilibrium. So same, maintain equilibrium means all the force equals 0, all the moment equals 0. And in this case, because you know that it's virtual work question, so you only need the virtual work equation. Okay, unless you cannot find, then you go back to force equals 0, moment equals 0. This one, it maintain equilibrium, or it will force you to use principle of virtual work. You only need to focus on work. Mean to find the small changes of distance. Ignore the mass of the member, so no W. No W for the arm. No W for the arm. So can you draw the free body diagram? Can you draw the free body diagram? He asks you to what? Coupled moment needed. M. This one. He asks you to find M. So change the whole system into D point, B point. A point, B point, it depends. Right? A point, B point. But you know that there's a support here. So there's a pin here. So cannot move left, right, up, down. So there is a 2 force in D, 2 force in B, Bx, By. Then what happened to this object if you let go from rest? How will it behave? It will rotate left or right. If you take out this moment, you let go of this, your hand here, and they given a W. What will this object behave? It will rotate clockwise. It will collapse like that. So collapse like that. So you need to draw before and after the diagram. So this one, this whole thing will move down. This one will move to this direction. Then it asks you what moment. So moment, you need to find the changes of angle. The changes of angle. Change of angle multiply moment, great work. Okay. Then translation also do work. This one, mass of this one do work. Go down, but this one go down, so positive work. Okay, weight and the distance traveled, it go down. Same direction, positive work. Okay, ignore the weight, so it's quite simple. So you see before and after. So you draw a diagram before and after. So this one, the back one, you can, when you draw diagram, you can just use a dash line to represent the original position. So your free body diagram, you only need to draw the after you let go your hand or from the rest. So you have a weight here. You just write W of object A. For example, this one don't have A, so you just write a W. Remember from the center, two forces here, right? Go up positive, go left positive, and this one is just pointing in, just all right. Okay. Okay. Then you put in the delta theta here. It will rotate delta theta. Here also rotate delta theta. This one will move down delta YE. It will move down delta YE. Okay. Then you see the thing that do work. These two do not do work. Cannot move. Only W do work. Okay. Only W do work. But he asks you to find the M. So include your M in the equation. Okay. You see how's the equation. So virtual work, you calculate what is YE and so on. Then you look at the equation. Virtual work, you write partial differential, this one, delta, U equals 0. This one costs you 1 mark. Okay. Then you look at the diagram. Moment do work because rotation. Moment multiplied by the delta theta minus W W Y minus, because this one is pointing up positive. Yeah. Y minus because your reference go up positive. In this example 3, why there's a negative? Because in your diagram positive go up. This one in the diagram your positive go up. So you get the negative work from the W. Yes. No. Let me find out. I already forget already. Let me find out. Okay. Let me confirm the information. Okay. Yes, I think we do the partial differential. We do the differentiation from the previous one. If not mistaken. So sine become cos, and then this one is U and V, right? You multiply sine and then you differentiate the delta. But let me find out. Let me find out the confirm this one. Right? You solve, substitute this one in, then you know that delta theta cannot be 0. You arrive at 1. You can sub out the thing, because if you put this one here, you have delta theta here, delta theta here. You factor out the delta theta. You know that changes of angle cannot be 0. So another part of the equation will be 0. Understand? So you're solving linear equation, then you find the moment. Okay. Example 4, your homework. Go and see, all the answer is there. Okay. Okay, we stop here. Okay, stop here. Tomorrow your test, huh? Yes.